So, good afternoon, everybody. So, today you have the pleasure to receive Dr. Melissa Graham as the speaker of our weekly webinar. So, Melissa obtained her PhD in astronomy at University of Victoria in Canada, and her main research interests include the study of supernovae, especially those of type 1a. And since 2016, she joined the largest synoptic survey telescope team at the University of Washington as a research staff scientist. And currently, she is a project science analyst and works with the LSST data management team. Today, Melissa is going to give a webinar talking about the LSST data products. So, Melissa, thank you very much for accepting our invitation to give this webinar. It's really a pleasure to receive you here. We are very interested in what you have to say about the LSST data products. So, please feel free to start your presentation, okay?
Okay, thank you, Jaderson, for that great introduction, and thanks everyone for coming to this talk today. I've prepared a talk that's going to be in 4 basic parts. The first is just sort of an overview of the LSST in terms of hardware and survey. The second part will really get into the data pipelines and the data products that are going to be created. And then the third and fourth parts will cover open opportunities to propose special programs for the LSST, and then also the methods for communication between LSST project and the science collaborations and the community in general. So I'm going to speak in each of these 4 sections, and then I'll pause for questions after each of them so that we have time to chat. So starting with an overview of the LSST, the main science drivers for the LSST are cosmology, the Milky Way, transient and variable phenomena, and also solar system small objects. So LSST aims to develop a telescope and a survey to make major advances in each of these 4 areas of science. It turns out that a lot of the major advances in these fields can all be met by a deep, wide area, multi-band survey of the full southern sky with an 8-meter equivalent telescope that does 30-second exposures all night, every night, approximately for 10 years. So that is what the LSST is, kind of in a nutshell. So these are the science goals that drove the design of not just the survey and the telescope, but also the data products that data management is going to be providing. So things that we will get deep into today, such as the prompt difference imaging, real-time alerts for transients, plus all of the deep coads and source catalogs for the full southern sky. This slide gives an overview of the LSST survey design mostly in terms of hardware. So at the top right hand, you can see the primary mirror size, the field of view, about 10 square degrees, the pixel size, and the filters, which will be UGRI, Z, and Y. And then under that, there's the main survey parameters. So things like the depth that you get in a single visit, the final depth of images after the 10 years of the survey, how many visits per field are in each of the filters from U to Y, and the full final survey expected area of 18,000 square degrees, and a comment that first light should be in 2020, with the official start of survey operations in 2022. And over on the left-hand side, you can see some schematics of the telescope up at the top, the camera in the middle there with a person for scale, and Cerro Pachón, the site in Chile, which is starting to look ever more like the schematic diagrams that were drawn up before the building started. So these are pictures of the site from yesterday, where we can see that parts of the dome are starting to go up now. And also I've seen pictures from the inside of the building, which is now completely finished and looks like a real building and is ready to have computers moved into it. The camera itself, this is what the focal plane looks like. And we often refer to the camera as being made of individual rafts. So each 3x3 CCD is called a raft. And the commissioning camera, which will be on summit, expected in late next year, will be a single raft. So just one of those 3x3 CCDs. And then the eventual full science camera, it's 2 different companies are supplying the CCDs. Of which I don't remember how many have been delivered, but so far a bunch have been delivered and are in testing. Then camera integration will happen sort of from 2019 through 2020, and then it's expected to arrive on the summit in early 2021 for commissioning and science validation. In terms of survey design, so far I've only mentioned that it'll cover the full southern sky with 18,000 square degrees, but you may have heard that the exact cadence and how the survey will proceed is still an open question. So the issue is that sort of a basic or universal cadence leads to a repeat time scale of 15 days in any single filter, such as R-band. And so what you're seeing in these 2 images, at left is a map of the sky that's showing the median internight gap. So that's sort of the recurrence rate of returning to a field in a certain amount of time. And then on the right, you're seeing that median intranight gap just for the R-band. So this is, so you're coming back to the same field every 3 days in any filter, but 15 days in a single filter, which is fine if you are only concerned with maybe deep stack science, such as photometric redshifts, but it's not great for supernovae. And so the community has really come together in the last couple of years to analyze different options for observing strategy. One of the most popular proposals is what's called a rolling cadence, where instead of doing the whole sky and then return and do the whole sky sort of every 3 nights, you would concentrate more and so repeat the same area more frequently, say maybe a third of the sky more frequently, and then do another third of the sky and then another third of the sky to get a higher cadence on a given field, so that, for example, your supernova light curves have more higher frequency sampling. So right now, this is still an open question and an active area for investigation between the community and the project. And I wanted to draw your attention to the paper that was posted on the archive in August that's called Science-Driven Optimization of the LSST Observing Strategy. And this is really meant to be more of an ongoing study. So as the project creates new observing strategy simulations, the community takes them, analyzes them for their particular science, and then reports back saying, yes, this would be much better for my science, or no, this is going to be detrimental to my particular science case. And this process of refining the observing strategy is expected to happen straight up through until the start of operations, and maybe even after. This particular image gives you a kind of a nice example of the expected improvements over, for example, what we saw with the SDSS in terms of sky survey image quality and image depth, just to highlight the improvements that the LSST offers. So we have examples such as the depth, you get more sources at higher redshift on the left. In the middle, an improved resolution leads to better deblending. And then over on the right, more low surface brightness features from this deeper survey. And then also at the top left, it mentions the number of nightly alerts and the final sizes of the source catalog. So trillions of measurements for billions of objects in the southern sky. And all of these nice images and a full sort of summary of the LSST survey can be found in Ivizic et al. 2008, which is on the archive, which is also a living document that's updated every couple of years with the latest plans for LSST. And I put a link to it at the bottom of these slides. So that ends our sort of survey, like really brief overview of what the LSST is going to be. So right before we really dive into pipelines and products, I'm just going to pause and like count to 15 and see if anyone has any questions about LSST in general.
Just a quick question. Yes, Felipe here. Yeah, I noticed that something that I've never seen, that it will saturate in magnitude of 15 depending on the filter. So that's correct. So objects brighter than that we will not see from LSST. That's correct?
That is correct. Yeah. Yep, the saturation limits were on maybe the second or third slide there that I had.
Okay, I've never seen, so just to be sure. Thank you.
Yep. Yep.
I do have a comment. I have a question actually. I understand that one of the goals is to observe variable objects in the sky, but I have a question. If observing the whole sky every 3 days or observing a smaller region more frequently will have impact on other science goals of LSST, or if just a matter to discuss what is better for variable objects?
Yeah, so it's mostly the variable and transient community that's driving the consideration of the rolling cadence and higher frequency sampling. And there are some reasons why some other science might be hurt by that. For example, if your science is sort of more like weak lensing and you want really deep, very uniform sky survey maps over the full survey area, then doing more of a uniform cadence where you build up very regularly can potentially help protect your final product from the influence of things like weather patterns that might impose like large scale differences in image quality across the 18,000 square degrees. And so this is why now LSST is making these observation simulations that are things that the transients and variables community would like to see, so that the sort of static sky science community can take them, test them, and then make sure that it doesn't hurt their science. Does that kind of answer your question?
Yeah. Great. Thank you.
Okay. Okay, thank you. Those were really good questions. And I also wanted to point out the first one about saturation. I do list some saturation values on that slide, but which you can sort of take and use as approximate estimates, but I don't know that they are exactly correct. And I'm also not sure exactly what the nonlinearity sort of behavior of the CCDs are going to be like around the saturation limit yet. And that's still sort of being studied with the new CCDs in testing. So just as a note there, that's not sort of the final, those may not be the final saturation values, and they don't say anything about nonlinearity. So just as a note. Okay, I'm going to move on. We're going to get deep into the LSST pipelines and products review. And I just realized I don't have a clock. So, okay. Just want to make sure we don't go too late. Okay. So the LSST data management team is responsible for the images from when they come off the telescope all the way through to when a user is attempting to do their science. So everything that happens to that image in between falls under the domain and the responsibility of data management. And so this slide kind of represents the three basic sort of areas of responsibility for LSST data management. The first one over at the left is the LSST data release data products via annual releases. And that'll be 11 data releases over 10 years with a final database catalog of 15 petabytes. And this includes all the individual images, stacked images, and source catalogs that we're going to talk about in this section. Over at the right, we have the prompt data products. And hold on just one second. Much better, okay. And then over at the right at the top is the prompt data products via the alert stream with an average of 1 million alerts per night with a real-time latency of 60 seconds. And we're going to talk all about what an alert stream is and what the components of it are in this section. The third thing that the data management team is responsible for is the LSST science platform, which is going to serve as both a portal to the data, a toolkit of notebooks and codes to use, and will also be capable of web APIs. So this is all how the data will be accessed, and we're going to talk about that also in this section. So within the LSST data management team, which is about, I think, 80 people by now working on all aspects of data management, there is something called the system science team. And I just want to bring it up because that is where I do my work. And so the system science team is responsible for the scientific validation of the planned data management deliverables to ensure that the data management pipelines and their products are designed to meet the overall LSST science goals. And the way that we do that is to work with the science community to better understand their needs and how they will be met by DM, by data management. We also identify scientific opportunities and risks related to the DM subsystem and initiate change. So anywhere where there might be an issue or a data product that might not be completely sufficient to do some of the science, we try to find those now and make sure that we fix that. And then also sort of on the flip side, to evaluate the scientific impact of proposed changes to DM deliverables. So things, for example, like how much storage is allocated to special programs data, for example, and what kind of science that would enable or inhibit sort of from a user's perspective. So that's where I do most of my work, and that's also why I tend to give a lot of these kinds of seminars, because I'm always interested in hearing from the community what is the kind of science that they're going to be doing and how do they sort of expect to do it and what do they need to be able to do their science. So this is why I like to give these kinds of talks, to tell you all about what data management is doing. And everything that I'm about to tell you about the pipelines and products is actually available in publicly accessible documents that I've sort of listed here. And on the right side of this slide are links to every single one of these documents that sort of go through all of the requirements from if we want to have this as one of LSST's main science goals. What are all the things that we need to produce as a data management team to make sure that that is possible? And in particular, I want to point out the LSST data products definitions document, often called the DPDD or LSC 163, is particularly useful and something that if you're going to be using LSST data products, you'd probably want to look at. So the data products in general can be divided into 3 categories of prompt, data release, and user generated. And if you've been around LSST in a while, you'll know that those used to be called level 1, level 2, and level 3. So the prompt data products are everything that is done in real time as the images are coming off the telescope. And it's often called difference imaging analysis, or DIA for short. And the prompt data products are all of everything that comes out of DIA, so difference images, the stream of time domain events that are produced in the night, which we call alerts, and also the catalog of orbits for approximately 6 million solar system objects. So that's prompt, it's everything that sort of happens in real time. And then the data release products are the maybe more traditional sort of annual reprocessing or processing of all of the data to make deep co-added images and deep source catalogs and object catalogs. And so the final sort of data release will be about 7 trillion detections, or 30 trillion measurements for about 30 or 40 billion objects, 20 billion galaxies, and about 20 billion stars are what's going to be in the final data release. The third level we call user-generated because it's sort of user-produced or added value data products or anything else that users might need for their science that DM does not make. So specialized reprocessing of certain fields that are of particular interest to your science, for example, or stacking. You don't want a single deep stack co-added images. You want them in, for example, like 6-month blocks because you're looking for faint, slowly varying objects or things like that all fall under the category of user-generated data products. And I know that there is a Brazilian partnership for LSST, but that we might have people who don't have data rights on this call. So I wanted to go over what is a world public data product versus what is a proprietary data product. So the world public ones that LSST produces means that they can be shared with anyone, with or without data rights. And sort of the three main categories that fall under world public are first the alerts, because the full stream will be delivered to a limited set of community brokers, which we'll talk about more in a moment. And those brokers can share the alerts with anyone. The second thing are the data releases after 2 years, which become post-proprietary and could be accessed through collaboration with data rights holders or by paying the cost of shipping and handling, because these are going to be very sizable data releases. The third thing is any education and public outreach data. So usually these are limited subsets that are used for citizen science. In the proprietary data category, proprietary data means that it cannot be shared and requires data rights to be able to use or publish. The first is the alerts database, which is an archive of all issued alerts to date. The second are the prompt images and catalogs, such as difference images and source catalogs that are created and made available in real time, which I'm going to talk about in a lot more detail in a moment. The annual data releases for the first 2 years. And then also the LSST Science Platform, which serves as a data portal, analysis toolkit, help desk service, contains access to computational resources for user processing, and an alerts filtering service is all considered proprietary and available to data rights holders only. So before we go really deep into the pipelines and data products, I want to take a moment to define some terms that get commonly used in the survey. The first is the concept of a standard visit, which refers to a single LSST observation of a single field, and will typically be something like 2 15-second images of that field done at a single time. And then the processed single visit image is the reduced combined standard visit images that were just taken. So that's processed single visit image. A template image is a transient-free co-add of probably about 6 to 12 months in depth. And so this template image, which is sometimes also called a reference image, is the one that gets used in difference imaging to compare with. Every new image is compared with this template image and subtracted from it to look for things that have varied since the template image. The term co-added image is also the same as saying a stack of images, for example, a median combined stack. So co-add and stack mean the same thing. When I refer to DIA, I mean difference image analysis, which we're going to talk about, I think, on the next slide. That just means you take your new processed single visit image and your template image, and you subtract one from the other, and then you look for any leftover sources that indicate variable or transient objects. The term DIA source means a single detection on a single difference image, whereas a DIA object is an association of all DIA sources by coordinate. So that's how LSST uses source and object. And that's not the same for every survey, but that's how we use it here. And then an alert means a packet of information about a DIA source that had a signal to noise ratio of greater than 5, and that's in positive or negative source. So that is any object that has increased or decreased in brightness since the template image. When I say DRP, I mean the data release pipeline. So that is the annually run pipeline that creates, for example, the co-added images. And here also we use the term source and object in the same way as we do for the difference imaging analysis, where source refers to a single detection on a single image, but object refers to an association of sources by coordinate on the sky. The third term is forced source, which refers to aperture photometry in a single visit image at the location of an object or a DI object or any sort of user supplied external object where you want to always have aperture photometry. And this forced source magnitude and properties of the forced source get done regardless of its signal to noise ratio, unlike the signal to noise ratio of 5 that gets imposed for creating a DIA source. So that was a bunch of just definition of terms that I'm going to talk about more in the next couple of slides, but I wanted to say them first so you get sort of a brief understanding first, and then I'll explain them more in context, and then hopefully they'll make even more sense as we go through the next couple of slides, starting with the difference imaging analysis and the alert generation pipeline. So sort of the first thing that happens to a single visit image when it comes off the telescope. So all of the following steps happen within 60 seconds of the shutter closing on a standard visit. So that single visit image gets processed and differenced with a template. Any source detections on the difference image that have a signal to noise ratio greater than 5 they are detected. They become a DIA source. From that stage, the DIA sources get measurements and characterizations done, such as measurements of their PSF, their flux, their shape, all that kind of thing. Then the DIA sources, all the new ones, are associated by their coordinate with either an existing DIA object or solar system object. And if that new DIA source that was just found in a difference image can't be associated with a known object, it becomes a new object. So that's how new DIA objects are created in the catalog. All of the DIA objects that have a detection in the past 12 months get forced photometry on this new image that just came out of the telescope. And all of the DIA object characterization parameters are now updated based on all of these new DIA sources that have been associated with them, such as variability parameters. At this stage, it's time for an alert to be issued to the stream. So that's one DIA source, so one new detection in a difference image goes to one alert. And we're going to talk about what's in an alert packet in the next slide or two. Also within the 60 seconds of shutter close, all of the DIA catalogs are updated in the US Data Access Center. So that means if you are using the Science platform and you are logged in, you can have access to these new updated DIA object catalogs sort of in real time. After that 60 seconds of shutter close, after all of this happens, there are a couple of tasks that are completed with a longer latency. So that's within the next 24 hours or by sunset of the next day. These are including things like force photometry in the past 30 days of images for all new DIA objects. So if a DIA source was found at a location where nothing has ever been seen before, it'll have force photometry done automatically in the last 30 days. All of the processed images from the night become also available in at least the US Data Access Center. And also the moving object pipeline software, which is commonly called MOPS, runs in the day on the DIA source catalog. And what it does is it links detections together to identify moving objects. So these catalogs that I just mentioned, DIA source and DIA objects, I mentioned that a bunch of measurements get done for the sources and the objects, and I just wanted to go into a bit more detail of exactly what gets measured. And a full and complete list of what gets measured can be found in the DPDD with the link at the bottom, or you can browse the database schema for these catalogs at the link that's given at the bottom of this slide. So for every DIA source, you measure things like the coordinates and its association with the DIA object or solar system object. You get things like all of the relevant timing information, like the time at mid-exposure at its location on the CCD, because the shutter does take time to move across the focal plane. You get the flux in the difference and in the visit images, and those fluxes come in PSF and aperture fluxes. All kinds of shape measurements are also performed, such as is it trailed, is it a dipole, what's the full width half max of the source. And then if deblending is run, any parent-child deblending flags are also included in the DIA source catalog for every single DIA source. In terms of the DIA object catalog, you have more sort of things like time averaged coordinates, anything about parallax and proper motion that's measured from all of the DIA sources that are linked together to form this DIA object. You get all of the fluxes by filter, time averaged, and then also in terms of the single visit, so the light curve, basically. You can, there will also be periodic and non-periodic variability features automatically measured and updated in real time for the DIA objects. And then DIA objects are also associated by coordinates with data release object catalogs. For example, if your DIA object is a supernova, it can be associated with the nearest couple of galaxies that were in the data release object catalog, so that you have a link directly between the variable object and its host. So I mentioned that an alert packet gets produced for every DIA source with signal to noise ratio greater than 5 in a difference image. And so this slide attempts to answer the question of what is in an alert packet. So an alert packet is basically just a formatted text file containing both the schema and data. And that data is the full record of the triggering DIA source. So everything I just told you that's in the DIA source and object catalogs gets into the alert packet. You also have the last 12 months of the DIA source record, so a sort of a recent light curve or recent behavior for this particular object. And then the matching object identifiers from the latest data release, so a link to things like the host galaxy or the star that is variable. And then aside from all this text-based data, there's also the image stamps. So at least 6 by 6 arc seconds, but it will be bigger if the source was bigger. And it includes both the difference image and the template image that was used to create the difference. And all of that comes in an alert packet. I mentioned before that the destination of alert packets is not individual scientists, but to alert brokers. And so the second panel here describes what is an alert broker. And they can be described as sort of the primary endpoints for LSST's event streams and how users will classify and filter events into subsets for their science goals. So the community is very active right now in building several alert brokers that will ingest alerts, do things to the alerts such as classify them, maybe prioritize them for spectroscopic follow-up, and then make that alert content available for users to either filter on or use them to cause other actions to go forward. Additionally, LSST, the data management team, will provide a basic limited capacity alert filtering service via the science platform, which is commonly called the mini broker. The next slide is just a brief overview of what MOPS does. So I mentioned before the moving object processing software runs during the daytime. and it uses all of the DIA sources that have been discovered that are not static, so not linked with a DIA object. And what MOPS does is links the detections together to find moving objects. It uses orbital fits to reject like things that have been linked together that aren't truly the same moving object, and also interfaces with the Minor Planet Center for orbit refinement. So if it's a known object, for example, it will be able to identify that it was a previously detected asteroid, for example. And then it also provides a lot of measurements and parameters for the moving objects, such as orbital parameters, the mean absolute magnitude per filter, and things like the G1 and G2 slope parameters for moving objects. So I've been talking a lot until now about the data products of the difference imaging and analysis, the DIA object catalog, the difference images, that kind of thing. And I want to point out that there are actually two versions of the products of difference imaging analysis. So far until now, we've been talking about the prompt versions, which are updated in real time with every readout. All of the, for example, DIA object variability parameters are based on just the past 12 months of data. So this prompt version of the DIA products are like a living data product that sort of only has a 12-month sort of memory window as it goes. And yeah, and this one is meant to meet the science needs of real-time follow-up. Annually, when the data release is made, all of the images to date will be reprocessed with difference imaging analysis using the latest set of codes to create sort of a, as of year 5, or whichever year we're in, these are all of the DIA products up to the year to date. So in this case, in the data release version of the difference imaging and analysis products, for example, variability parameters are based on the full survey to date, not just the past 12 months. And then this data release version does not get updated in real time. So this version is only updated on a yearly time scale. And these two different versions of difference imaging and analysis are meant to meet different science needs. So as I mentioned before, the prompt one is more for real-time follow-up, whereas the data release sort of annual versions are going to be better for things like rates. So like supernova rates in different types of host galaxies and things like population studies of variable stars. So depending on what your science goals are, you would be using probably just one of these two. And that's a good segue now into the data release pipeline. So the annual data releases and processing that are released. And in terms of the images that are produced for this, it includes things like all of the raw data and the calibration frames, the processed single visit images that we talked about before, and then also the stacked images, also called COADs. And these will include short period ones, such as yearly and full survey to date. They will include both the best seeing stack and the deepest possible stack, unless those two can be shown to be equivalent. There will be stacked images both for every filter individually and also multicolor stack. And also the transient-free template images that we mentioned before will also be produced on an annual basis. The catalogs that are produced in the data release pipeline are similar to what we've been talking about before. So the source and the object catalogs, where the sources are in the individual images and then objects are associations of sources at a single set of coordinates. And the measurements that get made for the source catalog are similar to what are made for the DIA source catalog. So the information includes things that you would expect like coordinates, fluxes in single visit images, and also in the deep stacks, any deblending parameters. And now since we're sort of not limited to or not dominated by point sources in the deep stacks, things like model fits, so bulge disk models, exponential models for extended objects, surface brightness, and color are also included in the source catalogs. And then the object catalogs that are released from the DRP pipeline are things like all the association of sources plus force sources. So every single object, whether it was detected just once in a single image or detected in the deep stack, gets forced photometry in every single image that was ever taken at its location. The object gets similar characterization parameters as source in terms of periodic and non-periodic variability characterization, but also has things like photometric redshifts and proper motions and parallaxes. So that covers the prompt category and the data release category. And then the third one was the user-generated catalog or user-generated processing. And I just have a series of statements about that. So LSST, the data management team, will not write unique algorithms for reprocessing any main survey data. So if there's a science goal and it can't be done with existing codes, then LSST, it's on scope for them to write a new algorithm for that science goal. However, LSST will make the software stack source code available to the community for user-generated pipelines, and that's available either external to the LSST Science platform, so I'll have a link to where the software stack can be obtained later on in the talk, but then also just if you have data rights and you're using the Science platform, you'll be able to sort of take the different components of the LSST pipelines and maybe put them together in a different order to make unique science products for whatever your science goals are. And in order to make that happen, LSST has also committed 10% of its computational resources towards enabling user-driven analysis and data product creation in the US stack. So you will not have to download, if you have data rights, you don't have to download the data and then also buy a giant server or processor to derive your science products, but you can log into the Science platform and use the computational resources that have been allocated to do that. And so I just wanted to take a moment to discuss this Science platform in a little more detail. So the whole idea of having LSST data management devise a user interface is to bring the analysis to the data. So you don't have to download and run your own codes. You can use the Science platform, which is envisioned to be both a toolkit and a workspace and a portal to the data. So you'll be able to use things like pre-existing tools to browse the data, visualize the data, as you can sort of see over at the left, some common interface tools that you might have used elsewhere before. The components of the Science platform will look similar to things that are being used elsewhere. And then the Science platform also allows you to access these computational resources for running queries on the data or reprocessing any of the data that you might need to do. And that's all we're actually going to talk. I'm not going to cover the Science platform in great depth, but I will point you to demonstrations of how to use different Science platform aspects that are available now, can be viewed online. So this link here takes you to, I think, like a series of maybe 3 or 4 YouTube videos that show different aspects of the Science platform in action. And that ends sort of the very large bulk part of the talk, where I wanted to go over all the different pipelines and data products that are going to be produced, and then also how you'll be accessing them in the future. And so we're going to pause here, and I can take some more questions on pipelines and products before we move on.
I have a couple of questions, Lisa. The first one is, who's going to create the depth map, systematic map, masks, this kind of thing? Is it envisioned to be provided by the DM, or it's going to be in the specific working groups?
Did you say, I'm not sure exactly which products you're asking about.
They have the variation of the depth, the magnitude limit as a function of a position in the sky.
Oh, yes, I think, yeah. LSST does make them. I forget what they are called. exactly. But yes, I do believe that's a data product.
It is a data product
I
from the end. Okay.
think
And the other thing is, how many official brokers are there already? I understand that Chile has one, NOAO have one, right?
yeah. So right now, out in the community, I think I've heard of about 5 that are currently in development. And right now, from a project side, we are currently writing a document that is going to describe all of the guidelines for a broker and including sort of the eventual proposal process. So there are no official brokers yet. That's coming. Yeah.
But NOAO has a project on that, right? I don't remember the name.
Yeah, that one is called Antares, and it's been
Antares.
in development for the longest. Yeah.
Thank you.
Yeah. Any more questions about pipelines and data products?
One more question. I mean, once the data release is done, we can download whatever we want, right? To a locally, right? For instance, we can actually submit a query and make a catalog and download the catalog if you want. I think that 10% of the resources only available for processing will not be enough to handle the whole community. So that would be possible, right?
So yeah, so all of the data access will be through a data access center. And what might happen, so I guess it depends on how much of the data you want to download. If it's all of it, then that might not be possible sort of immediately. But downloading, so I did say that you don't have to download the data in order to do your analysis, but if it's some sort of moderate subset of images that you just want to download and have locally, then I think that is possible. Yeah.
You're also emphasizing a lot the US DAC. What about the Chilean DAC, which is a little bit closer to us? I mean, will it be possible to use too?
Yes, exactly. Yeah, though those two should be equivalent. I think the only difference is in sizing, just because they serve different size populations. But yes, so if you're in Brazil and you have data rights, you'll probably be accessing the Chilean DAC, which should be pretty much equivalent to the US DAC.
Okay, thank you.
Yeah.
So, hi, this is Ricardo Gando. A related question. If I want to set, let's say we would like to set up a partial DAC here, would it be possible to get just part of the products? I don't know, only catalogs, for instance? Or...
Yeah. Well, so that capabilities for that are currently being worked out for people to set up independent DACs and maybe just have, some subset of just the catalogs. And it looks like that's probably going to be an option, but the details aren't worked out yet. It's still in progress, but it's looking like that should be possible.
Okay, thank you.
Hi, it's Julio. I have a question. It was not clear to me whether you have a separate list with solar system objects having the names, I mean the non-solar system objects, if you observe with the LSST, at least having, for instance, positions, the observed magnitudes, etc.
Yes, so because the moving object pipeline system, the MOPS system, is going to interface with the Minor Planet Center, all known asteroids should be very easily identified in the, what we call the SS objects catalog, the solar system objects catalog.
Okay.
Hi, Felipe again. So to have access to the alerts, I mean, for all the alerts, not only the roads available alerts, we have to be working as a broker or with a broker. That's correct?
That's correct. The full alert stream, it's not possible to deliver it to individuals, so it's only going to go to a selected set of community brokers. Yeah.
And the brokers will be for all the alerts or individually for solar system, supernova? I didn't understand that.
Yeah, so brokers are sort of very free to define their own science goals and develop brokers, like develop a broker that serves or focuses on certain scientific fields, certain kinds of transients and variable stars. And so that is where, yeah, some science specificity will come into play. Yeah, I think that answers your question.
Yes.
So they are not compelled to actually deliver any kind of alerts. I mean, they might decide just to choose what they want to.
Exactly, yeah. So because it's the community that's putting their time in developing the brokers, there's no real, LSST will produce sort of guidelines for what they would hope the brokers would do, but there's no actual constraints on the brokers. However, the people who are developing the brokers, since there's only a limited number that LSST can provide the alert stream to, whoever gets selected, serving a broader proportion of the community will definitely be one of the criteria considered when selecting which broker proposals to send the alert stream to.
Thank you.
And it won't be a list of the alerts or sources or objects that if I have access to the LSST data, I can only go there and search. I have to be part of a broker.
No, so if you have data rights, you can access the Data Access Center and the Science Platform. There will be both an alerts database, so you'll be able to query the historical alerts. And there'll also be what's called a mini broker, which will provide some sort of limited filtering. So, and when I say filtering versus brokering, a lot of the brokers will be doing like very sort of complicated light curve fits or cross-matching with, for example, infrared all-sky catalogs, but the mini broker will be simply a filtering service that only uses the information that's already in the alerts. And so, but that will be available that you can go and set up your own filters within the mini broker. And so you might not need to work with a community broker if the mini broker can satisfy your science goals.
Oh, thank you. Fantastic.
Okay, are there any more questions about pipelines and products? Okay, so it looks like we are just with 5 minutes left. And so the last two sections that I have were actually quite short. And so I think that since I figured most of your questions would be about pipelines and products, which they were. So I think I'm just going to kind of skim through really quickly just to let you know about the special programs opportunities and then the data management resources for participation, because I think that you'll probably want to know them. And then I'll make sure that I finish exactly at noon. Jaderson, does that sound like a plan?
Yes, to me.
Yeah, okay, we can do that.
Okay, I'll skim through quick, and then if people have to leave, at least the most important things have been covered already, so.
Okay.
Okay, so I just wanted to alert you to the idea of a special program. And a special program refers to anything that's not part of the Wide, Fast, Deep main survey. So different areas, different survey strategies for that area, or for example, variations in what you do in terms of the visit image. So shorter exposures, longer exposures, that kind of thing. Since the Wide, Fast, Deep main survey is projected to be able to complete its science goals within 90% of the observable time, there's 10% extra time available for these kinds of special programs. And so over the past couple of years, people have been proposing different areas that would add to the science productivity of the LSST if they were covered as a special program, such as, for example, you can see on this plot, the North Ecliptic Spur, the South Celestial Pole, the Galactic Plane, and then some deep drilling fields, which are sort of the dark red circles on there. So right now, the community has been talking about different kinds of special programs, and coming this year, in June, there should be a call for new white paper proposals for different kinds of special programs. And anyone can write a white paper proposal. They will all be sort of collected together, considered en masse, and then new observing strategy simulations will be produced by the project that include these kinds of special programs. And then the community will be able to analyze them and say, yes, these would be especially good for my particular kind of science goal. And so with this part of the talk, I just wanted to alert you to what special programs are, and that this upcoming call is expected to be released in June with a deadline for white paper proposals in October or November of this year. And so I'm going to skip through a couple of slides that go into really deep detail about it, and just sort of move on to the community and how the community is preparing for LSST. Yeah. And the following couple of slides just sort of go through really briefly how to find out more information about LSST, or how to get involved if you are now inspired to join a science collaboration, for example. So this is sort of the main web page for the LSST that has a particular section that says for scientists on it, and also has different ways to participate. So you can come here to this website and look at all the different ways that you could participate as a scientist and get involved. There's also sort of, if you're looking for more of the information like what I just told you today, there's the For Scientists page, has a bunch of information like you can see over at the left about, for example, filter throughputs, if you're sort of interested in doing some simulation of what your type of objects would look like in LSST filters. I mentioned before that the software stack is available online and will also be available sort of as tools within the science platform, but is available now. So if you have done a sky imaging survey and you want to use LSST's difference imaging analysis to process your data, you can download the science pipelines now and use them. And this is the website that you would go to do that. And then I also want to point out the community forum, which LSST community is a web page forum that allows people, so allows for a lot of project community overlap and interface and talking about different aspects of the data pipeline. And in particular, we have this category that's called Data Q&A. So if you find yourself with leftover questions from today's talk, you can come here to LSST community, and under the science category, you can choose Data Q&A, and then you make a new topic and you can ask your question. And this forum is moderated by members of the Data Management Subsystem Science team. It's moderated by me, actually, and I will make sure that your question receives a timely and accurate answer. And we like to use community for this because then other people can come who have the same kind of question, search the database of all of the questions that have been asked, and potentially find an answer. And so this communication method is useful for those kinds of questions. And also I want to point out the concept of the LSST science collaborations. So these are community members who've got together by science domain and formed working groups. There are currently 8 science collaborations, and science collaboration membership, though, is limited to data rights holders. The science collaborations do a wide variety of activities, mostly helping to prepare for science with LSST. So they do things like having meetings over video cons or face-to-face. They also have their own forums for discussion on the community website. This is the collection of people who produced the Observing Strategy white paper that I told you about before. The individual science collaborations are building science roadmaps. So they take a look at the kinds of code and capabilities that they're going to want to have in place sort of for 3 years from now, and make sure that they have a map towards developing the code base and analysis tools that they will need to do science in the LSST era. Sometimes they do that by running data challenges for tool development. They also collectively assess the follow-up capabilities. So for example, spectroscopic resources that are available to the community to figure out whether they need more or less, or maybe different policies that regulate the use and prioritization of the follow-up capabilities. And the last thing I wanted to point out is that the LSST Corporation runs a data science fellowship program that prepares students for dealing with big data in the era of LSST. The LSST, the For Scientists page also has a bunch of very useful webinars about a whole wide range of data topics regarding pipelines, products, cadence, things like what is education and public outreach going to do, how will DM handle crowded fields. There are hour-long seminars with slide decks and recordings on all of these kinds of topics that you might be interested in. And then I just wanted to point out as the last thing, the 2 relevant future meetings. One is the LSST at Europe meeting that will happen in June. And then the second is the LSST Project and Community Workshop is going to be in August in Tucson, as it's in Tucson every summer, where members of the project and the community come together for a series of plenaries and breakouts, and sometimes even like and there's a hackathon, an unconference, all to sort of help better prepare for the LSST era. So, and that's everything that I wanted to tell you about today. So you can feel free to also email me with any questions that you have in the future, or use that community forum. Thanks very much.
Thank you, Melissa. So I believe we have time for 1 or 2 more questions. So in the audience, if we have questions.
Maybe a quick one, and still with the brokers. What is the link between collaborations, all the collaborations and the brokers?
So there actually isn't a direct link, I suppose. In the States, the Antares broker, because they are interested in transients and variables, there's a lot of overlap between Antares broker and the transients and variable stars science collaboration. But there's not like set up hard links or anything like that between. A lot of the broker development is sort of like associated with science collaborations, but not necessarily owned by them, if that's your question.
Okay. Yes, that's it. Thank you.
Well, I have another question. It's Julio again. It's not directly linked to the pipeline stuff, but what can you tell me about the astrometry on very crowded fields?
I actually, personally, I can't tell you much about, I don't have like the numbers or anything, but if you do go to the LSST For Scientists page, there is definitely one of those talks that was given by Jim Bosch about LSST capability in crowded fields. And I think that does have the answer to your question in it.
Okay.
And if you can't find it, definitely just try emailing me, and I can find you the answer.
Okay. Thanks.
Yes, you're welcome.
Do we have any other questions? So if we don't have any other questions, I'd like to say thank you, Melissa, for a great presentation. So let me share my video. Okay, so thank you very much for participating in your webinars. It was a pleasure to watch your presentation. So thank you very much.
Okay,
Thanks
great.
for the fantastic seminar. Webinar.
Okay,
Thank you.
great.
So
Was
thank you
awesome.
very much for participating, and thank you everybody for attending. So let's thank Melissa for her presentation.
Thank you very much.
So thank you everybody. Bye bye.
Bye.